Hey, Jonathan, welcome back.
Good to be back.
Yeah, and today's question, I know about your computer, but which white column database you will pick, but not Cassandra?
Besides
So,
Cassandra.
so what is your second choice,
Oh, can I pick one that's in a slightly different space? I
Sure.
would go with Apache Kudu. That's Kudu, and
Okay.
it's a bit of a less well known database that's designed to be able to handle both analytical queries as well as transactional queries in the same storage engine. So there's obviously some trade-offs it makes to be able to do both in the same engine, but it's a really fascinating design and an application of the wide column kind of design to this analytical
hmm
problem space.
Is it written in Java?
It is. It's been a while since I looked at it. I want to say it's written in C++.
Then it cannot compete with Cassandra, right? So no danger there. What I thought that you will pick a Foundation DB. I thought,
That's well, Foundation DB isn't that a key value database more
Yeah.
than
Yes.
wide
Yeah. You're
column?
right. You're right. But yeah, of course, it is a key value, but very fast one. But I thought, okay, you're right. Or Foundation DB. This was completely wrong. Or Dynamo. I thought you will pick Dynamo, but it's not open source, of course.
Right, and yes,
Okay. But today we have to talk about JVector. So we touched on that last time.
yes.
How it started and what it is, and maybe we should start just now with vector, because JVector, it stores vectors.
Right.
And is a vector just for Java developers an array of doubles?
Effectively, that's what it is. And so,
Mhm.
in practice, it's actually an array of floats, because
Floats. Mhm.
that's a better trade-off in terms of the space and precision
Mhm.
for machine learning tasks. But yes, that's exactly the idea.
Okay. And how long is such an array or vector? Or array, I think. Is it actually array, which I would pass to JVector, or is it a data structure, not an array? So is it a list, or is it
So it is an array. So that's going
Okay.
to give you the lowest overhead. And thanks to the latest changes in the Panama API in JDK 22, you can actually wrap an array on heap in a memory segment and be able to pass that to native code without having to copy it into a natively allocated vector, which is what you had to do in earlier versions of Panama.
Mhm. So what it already means to me is that I have to pass such vector a couple of times, to be, otherwise it wouldn't matter, right? If there will be a coarse grain operation, I could pass the vector once, and if there's 10 milliseconds or 2 milliseconds, overhead, no one will care. But I think if you work with a JVector, with a vector database, and you parse a text or whatever, so you will have, to interact a lot, right? With
Right.
such a
So
database.
the core operation in a vector search engine is comparing vectors.
Yeah.
So you're doing a dot product, or you're doing a cosine, or you're doing a Euclidean distance, and all of these are fairly heavyweight operations when your vectors are hundreds or thousands of floats.
Yeah. What I forgot, of course, because JVector is embedded. I think, okay, who cares? Because in my use cases, overhead doesn't matter. But if it's going to be embedded to Cassandra or Astra, it is completely different, because we could have 1,000 operations per second, right? So this is the
Yes.
difference. So for embedded application, I think it doesn't matter at all. But if you would use JVector in a proper database, then it's different, right? So then
Well,
it has to be efficient.
I think I'd push back on that as well, because if I had JVector embedded in IntelliJ and I'm searching through the vectors that represent methods in my
Mhm.
project, then
Mm.
I could have 100,000 of those, and I'm going to be doing 1,000 or 2,000 comparisons per search. And so, yeah, actually 2 milliseconds per comparison, that adds up quickly.
Yeah, you're right. So what you can save actually? So you measure that, the difference, Java 22 versus Java 21?
Yes. Well, yeah, the short version is yes. I don't have the exact numbers in front of me.
No,
but it is material enough that the next version of JVector is going to require JDK22 to use these native optimizations that we're writing.
It's like 5%, 10%, or something like that. Or...
I mean, it's close to 50% because copying a large vector is very expensive, and that's what you had to do otherwise.
Mm-hmm. How large are the vectors? I mean, how many slots the array has? So what is the length of the array?
Yeah, so to back up a little bit, the way these vectors are generated is you actually train a machine learning model on pairs of related or unrelated pieces of text. And so you break up an article into sentences that are from the same paragraph, for instance, and you would tell the model, hey, I want you to make these two sentences have similar dot products when we start using their vectors. Or I'll take two sentences from completely different articles and I'll say, train the model so that these are farther apart. And so you end up with these fairly large machine learning models that are turning arbitrary amounts of text up to a certain amount of size. So the common sizes for your text that you can digest. For the BERT model, which is one of the kind of the grandfathers of all of these, there's 512 tokens. And I believe that the latest OpenAI models are 8K. So there's kind of a range in there, but it's fairly large pieces of text. And then you're turning them into these sequences of floats that are anywhere from 384 is a small embedding model, and OpenAI's largest is 3072. So that's their V3 large model. Most people are using the OpenAI V3 small, which is half that size. It's 1536. And the OpenAI V2 before that is also 1536. So then you have Google's Gecko model is 768. And there's a couple models that do 1024. But that's kind of the range.
You know what Claude is?
Sorry?
The Claude, for instance?
I don't know off the top of my head if Anthropic has an embeddings model that's available as a public API. If they do, then I haven't used it.
Okay. Interesting. So the longer the array, the more dimensions the vector has, right?
Exactly.
So and dimensions would mean aspects we can consider comparing,
yes,
concepts, right?
Yes, and it's usually not as obvious as, hey, index 3 corresponds to this quality that I deliberately designed into it. That's why you're training the machine learning model to separate out those components for you, so it's more of a black box, but internally there is something that index corresponds to.
Yeah, of course, because if I have broad model, it has many dimensions, but I could be only interested in a subset, right? So then I have a huge vector, but I don't need the huge vector, right? So this is how basic.
Yes. And there's actually a research topic that's recently hot because OpenAI V3 started using it. They call it Matryoshka embeddings. And I hope I'm pronouncing that correctly. It's the Russian doll, where you have a doll inside a doll inside a doll inside a doll called Matryoshka. And with these Matryoshka embeddings, you train the model so that the first half of your embeddings are the most important, and then the rest of it is just kind of fine tuning it. So that lets you cut the vector size in half, or maybe by 25%, if space is more important than precision.
Okay. So, and JVector can deal with all sizes, or
Yes, it can deal with all sizes, and we have so the layer on top of JVector that decides what compression settings to use and so forth. In my code, that layer on top lives in Cassandra, but you could that it doesn't necessarily have to be that way. But the way we did it in Cassandra is that we have kind of generic settings that work reasonably well for everything. But then we found that to get the maximum performance, I actually want to have settings where I've fine-tuned it for the OpenAI v3 or for the BERT embeddings or for the Gecko embeddings. So we have half a dozen of those where we've tested it. And we have, you can say when you create the index, these embedding vectors come from this source model so that you know how to optimize it.
So the compression is, Matryoshka would be a compression, right? Because what only matters is the first part, or the if you read from left to right, this is the most significant information starts and then becomes less and less significant. So this is kind of compression, or
yes, that is a kind of lossy compression, right?
Okay, so there are other compression algorithms which matter, or
yes. So the most generic and the most powerful is called product quantization. And I guess let's start with the one that's less often used, but it's simpler. So the simple one is called binary quantization. So that just means that I have this array of floats, and each float I'm going to turn into a single bit. If the float is negative, then it becomes a 0. If the float is positive, then it becomes a 1. And that's it. That's binary quantization. And then when you have a vector of 1536 dimensions, then you can approximate the dot product of those vectors by just the Hamming distance between its binary quantized representation. So if the two vectors both have a 0 or both have a 1, then my dot product output will be a bit of a 1 in that index. But if they're different, then it will have a bit of a 0. Sorry, other way around. If they're the same, then it has a bit of 0. If they're different, then it has a bit of 1. And so that gives you this very lossy approximation of what that dot product is. And that actually turns out to be all that you need for the Ada version 2 vectors from OpenAI. They actually compress very well with binary quantization. But with the caveat that when you do that, it's lossy enough that your recall goes from 95% to 50%. And so what you have to do to make up for that is you need to search deeper into the graph. And then you keep a list of, if I'm searching for my top 100 vectors, I'll search for the top 300 using that lossy compression. And then I'll take those top 300, which represents, I probably did 3,000 comparisons to get those top 300. And now I'll re-rank those 300 using the original float 32s. And and I'll, after that re-ranking, then I'll get it down to the 100 that my user wanted. So that combination of lossy compression plus re-ranking, you can actually, it's effectively a free lunch, because not only are you saving memory and saving disk accesses by using that compressed version for most of the work, you can actually make your search faster as well, because doing that binary quantization comparison, it's just super, super fast. And so I can make up for having to do more comparisons by having my comparison function be 10 times faster. So that's
and 10 times faster. What I thought right now is, you said a float is replaced by a bit.
Yes.
So and float has 32 bits.
Yes.
So it means the compression factor is 32, right?
Yes, the compression factor is 32, And then
but we have to search 3 times more, right? And this is why you said it's 10 times faster.
That did happen to work out that way, yes. So you've got a couple things that are trading off. You've got the doing a dot product versus doing a Hamming distance, which
what is Hamming distance?
So Hamming distance means if I have a series of bits, how many of them are different between those two series.
Okay.
That's all. And one of the Richard Hamming. It's named after a physicist who kind of invented information theory, or was one of the inventors of information theory in the 1960s or so. And so it's named after him. Because what he was concerned is how do I optimally, if I have a set of items and I know what that set is, how do I optimally encode that in the smallest set of bits possible? So with very early network communication, saving even a few bits out of your message was really important. And so that was one of the things that his research focused on.
Recently, I found, I think it is called file diff in Java, where you can compare 2 files, and what you get, the first bit which is different. So similar, right? So this is if you have an array, so you say, okay, this is equal, and then when the difference starts, this is the Hamming distance?
The Hamming distance is the total number of differences.
Oh, okay. Total number of difference. I thought when the difference starts. No, the total number of the difference. Okay, complete different.
Yeah.
The total number of different bits.
Yes.
Right. So okay, this is why it is easy to find the difference. If you have just bits, you can
Yeah, and there's a method in the JDK where you can take a long array and say how many bits are different in these two longs, how many of the bits are different. And so that's actually how we implement it in JVector is the binary quantized representation of the array of floats turns into an array of longs, because that's the fastest way to compare them is 64 bits at a time.
Oh, so you're actually using the binary compression?
Yes, specifically for the OpenAI V2 vectors. That's where we found it performed the best.
And what you are saving is memory and CPU both, right?
So yes, actually. So the motivation is that vector search, like traditionally, let me back up for a second. There's kind of two categories of vector search algorithms. I'm going to partition my vectors into a series of subsets. And then at query time, I'll take the query and I'll compare it to the centroids of my partitions that I have. And the closest in partitions, I'll do an exhaustive search for everything in those partitions against my query vector. The second kind is you will actually build a graph instead. Instead of doing these partitions, I'll build a graph of my data set vectors. And then at query time, it's doing a breadth first search. And at every node in the graph, it says, am I getting closer to my search objective, or am I getting farther away? And if I'm getting closer, then I'll follow that farther. And so the reason JVector is a graph-based index, and the reason is that graph-based indexes are generally faster, generally more precise, and you can construct them incrementally. And so with the partitioning algorithms, I need to know my entire data set before I can construct the index. And so for when your application is something like a database like Cassandra, where I want to be able to insert a row and have that indexed immediately, the graph family of algorithms is much more appropriate. And so that's why if you look at the open source vector databases, all of them are graph-based. I can't think of a single exception. The only exception I can think of is the first version of pgvector. And everyone said, wow, this is really, really slow. And so pgvector switched to HNSW, which is a graph algorithm. So the only one I can think of that started with partition-based ended up switching as well. So JVector is graph-based, and I completely forgot where we were going with this line of thought here.
You started with the
partition. Memory, yes. So
memory and CPU.
The problem with the graph family is that because you have almost exactly the same probability of visiting any node in the graph as any other, then if you try to serve that kind of index from disk naively, then your performance is absolutely terrible. And so the simple way to deal with that is to just say, well, we'll just keep the entire index in memory. Obviously, you start to run into scalability problems with that sooner rather than later. And so the trade-off, the reason why you want, one of the big reasons why you want to use something like binary quantization is now I can do that first half of the search completely in memory. I'll just keep the quantized versions of the vectors in memory. I'll do my first pass of the search against that. And then when I get that 300 where I want to re-rank those with the raw vectors, I'll go to disk to get those. And so that's what an algorithm called DiskANN was the first ones to do this in vector search. I believe it's from 2019 is when Microsoft Research published the paper. And that's what JVector's based on. So I don't believe we were exactly the first, but we were one of the first projects to build around that and serve larger than memory data sets with that approach.
This reminds me of partition key and sort key. You have the partition key and you know where the database lives. So you can have your item collection. So it is you can scale linearly because you just go first. You find the database. It is limited, but there's some limit, and then you use the sort key to find a related object. So this is very similar concept in complete different area.
Yeah, and you could compare it to radix sort, for instance, as well, where you're doing like this bit. I'll do the coarse pass, and then I'll do a more fine-grained pass, more fine-grained. So yeah, there's a lot of parallel ideas in computer science, I guess.
So, but the compression, it is actually not a compression; it's more a transformation because at the end we get the same results, right? Because if we trade in, the length of the vector with the results we have to consider. So there is a trade-off. Trade-off. This is the result of the transformation. So when it makes sense not to compress, then,
Well, I would say that compression actually is a good way to describe it because it's like a JPEG compression where you are throwing away data, but you're hopefully preserving the most useful data to allow you to reconstruct it in a useful way.
Mm-hmm. So more almost like projection, right? So I'm
yes,
because
and people have tried. So there's absolutely a concept of projection in machine learning, and people have experimented with, well, what if we just do a principal component analysis of this vector to cut it down to a quarter or an eighth of the dimensions. And you can do that, but it turns out there's a more powerful approach that is almost always better, and that's called product quantization. So I mentioned that we use binary quantization for the Ada version 2 vectors. We use product quantization for everything else. And so the way product quantization works is you have your original vector that's 1536 components large, and you split it up into a number of subspaces. And let's say, for instance, that our subspace size is 16 floats. So you take the first 16 floats in across all of your vectors. So if I'm indexing 100,000 vectors, I'll take the first 16 from each of the 100,000, and then I'll do a k-means grouping of those vectors to get 256 code points that are the most distinct across those 100,000 16 element subvectors. And so now that once I've broken that down into the 256 most distinct code points, I can represent each point as a single byte. So I've taken those 16 floats, turned it into a single byte. So that's a compression of factor of 64. Next 16, single byte. Next 16, single byte. And so this actually works significantly better than a PCA-based projection. And so you actually can get 64 time compression and do useful searches with that. So we most commonly compress by 64, we compress by 32, we compress by 16. We've experimented with compressing something not by a factor of 2, but it hasn't been as useful in practice.
And this is how Olama and all the local LLMs are working, right?
So they're actually doing the PCA-based quantization. They're not doing product quantization. This is more of a vector search specific. Well, it's not specific to vector search, but it's very, very useful in vector search.
Otherwise, it wouldn't be usable on local machine, right?
Past a relatively small data set size, yeah.
So incredible. So what it means is the JVector can implement all of that, and it uses this disk ANNS. It is nearest neighbor search, and A is what?
Approximate.
A is approximate. Okay, published by Microsoft, and this is the trick that you find the coordinates, if you will, on the disk first, and then you search further, right? So this is actually the two-step process. So this is the entire trick in the disk.
Right.
Was it hard to implement in Java? So, or is this like one class, 50 classes? Is it like, a small piece of code but crazy complex, or more like, the architecture was the challenge? So what was the challenge implementing this?
That's a good question. I'd say there's the algorithm is pretty straightforward. I think that was probably not the most challenging part. I guess the first challenge you have whenever you're implementing an academic paper is like, what did they leave out? And so, for instance, things like how many iterations of k-means do you need to run to get meaningful results before you get diminishing returns? Or how many vectors do you need to have in your data set before you can do k-means in a statistically meaningful fashion? And so for a bunch of those questions, we actually went to the Microsoft Research repo on GitHub, where they maintain this in the open Apache license. And this is the implementation that powers Microsoft Bing. So I'm not sure if it's the most open source piece of code that Microsoft publishes, but if it isn't, it's pretty close. And so we were able to look at their C++ code and say, how did you tackle this problem, and borrow their answer as a starting point. So that helped a lot. And so many thanks to the people at Microsoft Research, if any of them are listening. The other thing that was challenging is just I think the big part is kind of self-inflicted. I think I mentioned last time we talked that JVector is the only vector search engine that I know of that uses optimistic concurrency control instead of pessimistic locking. So I think that was probably the most challenging from an implementation standpoint, is that we kind of had to invent that nobody else was doing, and understand the algorithm at a deep enough level that we could be certain that what we were doing was correct as well as fast. So yeah, I think I'm substantially proud of the work we did on that. And then I guess the third thing is like, okay, we implemented DiskANN, and now what, right? Like, how do we drive the state of the art forward and not just imitate something that somebody already did in C++? So we've been working on that for a few months now, and we'll have some results to announce in the next couple weeks, I hope. I don't think I want to spoil it here, but we'll announce JVector version 3 soon, and talk about what we've done beyond DiskANN.
Okay. Good, how to call it? Good artist copy, great artist steal, right? So you look at the code, and now you are the great artist. You have to make your own and improve it, right?
That's right.
Yeah. Very very good actually. So what it means is we have a very new algorithm. 2019 is nothing, right? It's 5 years old.
That's one of the things that's so exciting about this space. So I mentioned that JVector switched to a graph algorithm called HNSW. HNSW was published, I don't remember if it was 2016 or 2017, but then that inspired DiskANN in 2019, and people have been building off of those more recently. Like, this is just, it's like an under 10-year-old field, and nobody knows like the answers to a lot of the most important questions. Like you mentioned in Cassandra, we know how to partition a table in a way that I can horizontally scale effectively, infinitely, with very low overhead. Nobody knows how to do that in the vector space, because the problem is that you, like, if you imagine partitioning a two-dimensional space into squares, right? You can do that, and then you can just say, okay, I'll just search this square that it falls into, but the closest neighbor might not be in that square. It might be in the one that's across a boundary in a different square, or across a corner into a different one. And so imagine that in way more dimensions. And so, like, yeah, it's a wide open research field for solving problems like that.
It sounds like the end of Interstellar, right? You know the movie?
I'm afraid I didn't see it.
You have to. This is the homework assignment.
Right.
You need a break from. It's a great movie actually, Interstellar. In the end, there was some an scene about multi-dimensionality, and this was interesting how it looked like. So this is why. Okay. First, vielleicht is German. Maybe for me and listeners is how the API looks like of JVector. It's just vector in write for indexing and then comparing. This is just like two methods, or you have 20, 50 methods, or how to imagine how it looks like. It's more like JDBC, more like Cassandra API, JPA. So which methods do you have?
There's basically two methods that you need to care about.
Okay.
Is add a node and search for a vector. That's
okay.
Everything else is details. And so if you look at the JVector project page, it goes into kind of the next level down on the details of how to use those, and how to set up a graph builder object that you can call add node to, and how to set up a graph searcher object that you can call search against. But it's basically just those two operations. And then you can get into like, well, how do I save it once I've constructed it? So it does get a little bit more involved, but fundamentally those are the two operations.
And which consistency guarantees do you have? Is this like read after write, or I mean, is it like optimistic means if I read, write, and read. So after the second one, I will see the data. So if there are two parallel writes, so one of them gets rejected, or what happens then?
So the approach we took is you can either I'm trying to think of the right level of detail to go into here. So when you're adding a node to a graph, the graph is directed. So if node A has an edge going to node B, the inverse isn't necessarily true. So when I add a new vector to the graph, then I need to figure out what edges should I connect from the node corresponding to that new vector, and what edges should I connect to that node. And so the problem with doing concurrent inserts is, if I do it the naive way, then one of those two nodes that I'm inserting concurrently will not know about the other, and therefore will potentially be missing an edge to it that it should have. And so the approach that we took with JVector was kind of a brute force approach, which is, as part of the construction, I keep a concurrent set of all the nodes that are in progress to being inserted. And so I will consider each of those as a candidate for adding edges to, even if I haven't found it in my search. So typically my search will come back with 100 or so candidates, and then I'll add to that 100 or so from the search, I'll add the 32 or so that I have, one per thread, that could be inserted concurrently.
And I get back to, you said hundreds of vectors back, but some kind of ranking, right?
Yes.
So from nearest, okay, so there's like a Java record with, I don't know, the, how to call it, distance and the vector, right?
Exactly. Although this is, as you know, when you're writing high performance Java code, you can't encapsulate everything in a class. And so everything in JVector is, we have an integer array representing the ordinals of the node, and then we have a float array representing the distances. Index 1 or index 0 in the index array corresponds to index 0 in the distance array, and so forth.
Okay. So, and also interesting stuff. So the more dimensions we have, the more likely collisions are, right? Or is it not true? Maybe not true at all, because the more dimensions the vectors are, then it is less likely that I'm operating in the same dimension, right? So what is true? Is there any impact of dimensions to collisions?
So the vectors are not intended to be like cryptographic hashes. And so they're not collision resistant in that sense. That said, it would be very, very unlikely to find two passages that independently encode to the same 1536 float 32s. However, as a database, Cassandra does need to handle that scenario, especially in the case where the user does want to have the same vector added more than once in different rows. And so the way we deal with that is we just have we use actually a concurrent skip list set for maintaining uniqueness. And then we have a mapping from that canonical set of vectors to, an arbitrary number of rows could be referring to that same vector. The reason why we use the concurrent skip list set, we don't actually care about the ordering, but what that does is it means that looking things up in the set is much less expensive, because the common case is that vectors are distinct. And so I only have to look at the first few floats in that vector before I get to an empty bucket in my concurrent skip list set that I can put that in. Whereas if I'm doing a concurrent hash set, I need to hash 1532 or 1536 floats, and that's expensive. That was actually a bottleneck that we ran into. And so we switched to a concurrent skip list set for cheaper comparisons.
Interesting. As you mentioned this way, what I had in mind, like a multidimensional vector or some kind of a multidimensional thing in the space, and there's another multidimensional thing in the space. And if there is an overlap between them and I update one of them, then I have maybe a problem, or two of them at the same time, right? And this is what I thought about. So try to visualize, what a collision means in such a database. And And what I thought is, okay, the more the dimensions we have, the more aspects we have, and maybe if we just update, interested in one subset of that, it doesn't matter. But I have still not to update the entire vector because I cannot patch it, right? I cannot say I only, patch this dimension and the others I don't care. You always have to send everything. And therefore, I think the more dimensions we have, the more problematic updates gets, right? So this is what you mentioned with the vector length, and I, try to tackle that from the, I don't know, visual perspective.
Right. And you're absolutely right that in the context of machine learning, it doesn't really make sense to update a single element in the vector. It represents something as a unit, and it's like the vector is the primitive of machine learning, even though it's not a primitive in Java. In Java, it's composed of float primitives.
Yeah.
But in machine learning, the vector is the primitive. And so, yeah, both Cassandra and JVector, you don't get to arbitrarily transform individual elements of the vectors. You have to change the whole thing.
Okay, so we covered a lot of JVector right now, right?
We did.
Very good. So so next question is, so I have my JVector. I embedded it, let's say, in Quarkus. This is what I use all the time. So and I use it in a typical, whatever it means, application. So I have no feeling how big such a vector database gets. Do you have a feeling already? So for typically enterprise use cases, or can we? I don't know. This is hard to tell, right? So what will happen? I think what happens first, that the relational databases are going to be vectorized, or whatever we call it,
Yes.
indexed with vector databases, right? And then they become. Then it is smaller than the original database, I guess, right? Because the vector compresses actually the actual data, right? So the vector, the vector is a representation of an image or a piece of text. We said, 500K or, right? So,
no, 500 tokens, not 500,000.
500 tokens,
yeah.
to 8Ks, 500
Yes.
tokens to 8Ks.
Yes.
This is what they said exactly. And what comes out is the largest vector is like 3,000 floats or something like that, right?
Yes. So
that is.
But when you're using it for retrieval augmented generation, that's the most common place to use this is you're building something with a large language model, and so you want to say, hey database, Jonathan's logging in to Netflix at 9 o'clock on a Friday. What are the most what are the most similar things that he's watched on the last month of Fridays? Like what does he like to watch on Friday evening? And so you go to the database and say, what's most similar to this vector? You pull that out and you say, here, large language model, Jonathan watched X, Y, and Z. What should I recommend to him? That's obviously not how Netflix recommendations work.
No.
They've got their own system, but you can imagine building such a recommendation.
And there was a
system.
competition, remember, in Netflix? So there was like competition, I don't know, 15 years ago, $1 million algorithm, $1 million algorithm competition.
But this is actually a good example, though, because Netflix spent tens of millions, maybe even hundreds of millions, perfecting their recommendation algorithm. And today I could make a pretty good recommendation algorithm with an API call to GPT-4 or to Claude 3 Opus and a small vector database of users' preferences. So I think that's why generative AI is so powerful, not necessarily because you can solve problems that you couldn't solve before, although in some cases there's that. But even if it's a problem that you could solve in 2020, the way you would have solved it in 2020 was with, 3 PhDs and, a huge amount of compute time to train a custom model. And now it's just an API call, and that's enough to get started. And maybe eventually you replace that LLM base with a custom trained model, but you get started so much faster and you can prove out whether the idea is worthwhile so much faster. That's why I'm excited about it. Anyway, coming back to retrieval augmented generation, if you're doing that with a database like Cassandra or like PostgreSQL with JVector, you usually have both the original data as well as the vector encoding, so that you can pull that original data back and give it to the large language model and say, now use this to ground your output.
The origin data, it would be enough to have a link to the data, right? So the idea would be that the origin data will remain in the database, and we have just the vector in the JVector database, right?
Right. And so my contention, as someone who founded DataStax and built the vector extensions for Cassandra, it's a much more productive way to do it is if you're doing it in the same system instead of trying to keep Oracle and JVector in sync manually. Use a database that does that for you.
Yeah, you're right. Just if people don't trust, let's say GPT or similar company to GPT, European enterprises, then they can use JVector with Cassandra and let's say GPT for as LLM. And this is more trustworthy because this is separated. I say this is my knowledge. This is just, it provides just the links, IDs or links which can be linked, right? If I have already a Cassandra, there's not an issue because I had a Cassandra before.
Right.
If I get or put JVector to the database, then this is just an additional index.
Just to clarify, Cassandra 5.0 uses JVector natively, so you wouldn't have to wire that up yourself.
Yeah.
Right.
But still, how big what is the largest? Let's just JVector. So if what is the largest amount of data you ever put to JVector, or what is what to get a feeling, because of course there are billions of records in strange databases. Most relational databases are not that big, but they are huge relational databases. How many vectors do you have typically in such a database?
So
what is a small database? What is a small database, and what is a large database?
Small is under 100,000.
Okay.
Medium size, I would say, is 100,000 to 1 million, and medium large would be 1 to 10 million. I would say over 10 million is large.
And the performance of JVector, is it like linear, or what is the performance characteristics?
It's a logarithm. It's n log n to construct the index, and then log in to search it.
Not bad. Okay. And how fast is it from the milliseconds in the largest? Rough numbers, to get a feeling,
Rough numbers. I don't remember with raw JVector. Once you add the Cassandra layers on top, rough numbers is 30 to 50 milliseconds.
That's still impressive. So this is like S3 is also 30 milliseconds without any AI. Just retrieve an object in S3, small one, costs you 30 milliseconds. So this is actually incredible. Okay, so I have another question, but this one would be we spent another hour. Because I wanted to ask, what would be the benefit of AstraDB over Cassandra? But this I will keep, maybe for another.
The short version is it's a hosted service. Like that's the advantage. Is some people would say that Cassandra is difficult to run and understand deeply, and so with Astra, you're outsourcing that to us.
And what I thought is that in Astra, the storage engine and the compute engine are maybe separated, or is it just Cassandra but hosted?
No, that's correct. We split Cassandra apart so that we could use S3 as our durable long-term storage.
Exactly.
Which is a good fit for Cassandra because, as you know, Cassandra's data files are immutable once written, and so that works out really well with an object store. And then we can scale the compute and the storage independently. Yeah,
this is what Neon, for instance, for Postgres also is doing, and most Aurora in the clouds is the new wave of database. I think all cloud native databases, they separate the compute from the storage.
You really have to, because of the way the pricing is done. That's the only way to get effective cost of ownership.
Yeah, pricing and backup, right? So also, because if you're using something like S3, backup happens. Just the disaster recovery, not backup. Backup would be point in time recovery or just an additional copy in a different region. But at least that the data is replicated for you. Replication, what you get for free, more or less. So in theory, could you also run AstraDB on Minio or something on OpenShift cluster? Should also work in theory, right?
In theory, yes. I understand from talking to our Kubernetes team that it's actually not quite that simple, and we actually have customizations for Amazon and for Google Cloud and for Azure. Okay. But yeah, in principle, sure.
Mm-hmm. Anything else we left off JVector, or we covered everything which matters to Java developers?
Oh boy. I guess I would just say you check out the code base if this is interesting to you. Like I said, it's a very young field. There's low-hanging fruit all over the place where you can do something that nobody has ever done before and make a contribution to expanding that field of human knowledge. The JVector code base is relatively small. It's very self-contained. We recently added a dependency to Agrona for primitive collections. But other than that, that's our only dependency. So it's very, very. It's probably the most fun you can have in a relatively small code base that's tackling complex problems. So yeah, check it out. Reach out to me if you're interested in joining the DataStax vector search team, and also, if you're not, and you read the code and you find something that, hey, this isn't as clear as I thought it should be, then let me know that as well. Because one of my goals is, when we're creating or releasing an Apache licensed open source project, is I really do believe that should be for everyone and not just for DataStax. So that's how we try to run JVector. Mm-hmm. And in fact, I'll give a shout out to our colleagues at Upstash, who were the second company to release a vector search as a service based on JVector. So we've got a existence proof that you can read the code even if you don't work with me.
So it also means that Upstash is a Java shop then,
yes.
Right? So kudos to them. They're very good. So also reasonable people, right?
Absolutely.
I found something interesting in JVector. So first, it uses Panama.
Yes.
SIMD and which is also, this is like a cutting edge technology. Yeah? You are using, the most recent pieces of Java, which is exciting already. I actually had a complaint at a conference. No, nothing happens in Java space. Java databases are disappearing, and I was proved wrong with JVector because it's absolute cutting edge and it's even better than the native competitors. And I had a nice conversation with Paul Sanders about Project Panama and also quantization. I think I pronounced this correctly. and maybe something like float 16 becomes part of Java. So this is in future, which will make JVector even faster. So this also, because I took a look at actually the code base of JVector, I found interesting. So there's a Panama, and this is really interesting project, I would say, for everyone.
Yeah, I'm very pleased that Oracle and Intel and Red Hat and everyone contributing to OpenJDK are driving it forward, especially on these lines of how do we leverage modern CPUs in the most effective fashion, right at about the same time as we need that performance for JVector. So really happy that the timing's working out for us there.
Perfect. Where people can find, on the internet, JVector, where they can buy AstraDB, Cassandra support, or whatever. So
yeah, I won't give I won't spell out the URLs, but if you just Google for JVector GitHub, then you'll find us there. Mm-hmm. And if you Google for DataStax Astra, you'll find our hosted database.
Yeah, thank you. And you, Jonathan, on where are you? Twitter, Blue Sky?
I'm on Twitter as Spiced with a Y, SPYCED.
Perfect. Thank you a lot.
Thanks again, Adam.